Hello, welcome to the lecture on reliability and accelerated lifetime testing in my Battery Management Systems course. Thank you for joining me in the transition to sustainable energy. Designing for the appropriate level of reliability affects cost. If we over-design for reliability, the product will cost more, reducing profit margins on every unit. If we under-design, the product may fail before its target lifetime, with corresponding warranty costs. I've split this lecture into two videos. This first video begins with an introduction to product lifetime and accelerated lifetime testing, then introduces the Arrhenius equation, which underlies accelerated lifetime testing. In the second video, we'll discuss some caveats of the approach. We'll see how to design a mission profile, and we'll touch upon the overall design and process flow. Okay, let's do it. Different applications have different lifetimes, and thus warrant a different amount of cost and effort behind the design and manufacturing. For example, a consumer good like a skateboard might have a 2 to 3 year lifetime. A phone might have a similar lifetime, though in practice I've kept phones longer than that. One website lists lifetimes of 4 to 8 years for iPhones and 2 to 3 years for less renowned brands. Cars are typically designed for an 8-year lifetime, and home appliances for 9 to 15 years. Estimates for solar panels and inverters vary, with 25 to 30 years being a common estimate for the panels, and shorter lifetimes for the inverters that convert between the solar panel's DC and the home's AC. To be clear, the design lifetime is a target for the minimum time that nearly every device should work properly. It is not a target for when devices should fail. What that means is that if the reliability target is met, at the design lifetime, some devices may start to fail, but likely many will continue to function longer. Importantly, the product lifetime is the minimum of the component lifetimes. Imagine you design a device where all the components last 15 years, except one, which breaks at 2 years. Imagine what fails is the connector. You may have a fully functional board that cannot talk to the outside world, or, in other words, a broken unit. Over time, that might look like this: a lot of failures shortly after the 2-year design lifetime of the component, with a few devices lasting longer, but very few are likely to reach 15 years. The lifetime of the least reliable component is the overall product lifetime, unless we've designed for some targeted mitigation, such as being able to replace or service that least reliable component. Testing is how we verify a design. So, how do we test for reliability? How do we experimentally verify whether the failures over time fit our desired targets? We can't just wait. The product cycle would be far too long. We emulate aging. We emulate aging by increasing temperature. To understand the concept, consider a cup of water with sugar. How long will you have to stir for that sugar to dissolve? What if it's ice water or hot tea? We've all probably experienced how sugar dissolves faster in warmer water. Generally, chemical reactions occur faster at higher temperatures. So, if aging is due to chemical reactions, increasing temperature accelerates aging. The Arrhenius equation quantifies this effect. To summarize what we just saw, application lifetimes vary with corresponding reliability needs. Increasing the temperature causes increased reaction rate, and this accelerates many aging mechanisms. If we model this well, we can emulate accelerated aging. That's the premise behind accelerated lifetime testing. Now, let's do some math. In this section, we'll discuss the Arrhenius equation. The Arrhenius equation is used in accelerated lifetime testing. It helps us translate between how much time in a hot thermal chamber corresponds to a product lifetime at a lower ambient temperature. For a moment, imagine a product with a target lifetime of 15 years. We can't just run a 15-year test to see whether we've designed our product well enough. we'll miss our market opportunity. Instead, we will place a pre-production version of that product into a thermal chamber and bake it to accelerate or emulate aging. The Arrhenius equation helps us calculate how long to bake. We'll look at the equation first and then apply it to this example product. The Arrhenius equation is an empirical equation which quantifies the rate at which reactions are accelerated by temperature. At a high level, the rate constant K is the number of molecules colliding per second and resulting in a reaction. That comes from the product of A, the number of collisions per second, and an exponential representing the probability of a given collision resulting in a reaction. Conceptually, the number of effective collisions is proportional to the number of molecules above a certain threshold energy. Next, let's talk about each parameter individually. K, the rate constant, is how fast the reaction or process proceeds, or as we said before, the frequency of collisions resulting in a reaction. A is the pre-exponential factor, and it is experimentally fit for a given process. We'll see in a moment that for purposes of accelerated lifetime testing, we don't have to know it. E is here because the probabilistic part of this equation is an exponential. EA is the activation energy. It varies by the type of process. In the context of accelerated lifetime testing, it varies by failure mechanism. KB is the Boltzmann constant. T is the temperature in Kelvin. Note that the Arrhenius equation also has another variation. Engineers and physicists tend to use the Boltzmann constant KB, while chemists use the universal gas constant R, with correspondingly different units for the activation energy, EA. Be careful not to confuse the rate constant K with the Boltzmann constant KB. Let's take a moment to notice the relationship between the rate K and the temperature T. Since temperature is in the exponent, a given change in temperature T causes an exponential increase in K. Let's now apply the Arrhenius equation. We start with asking, how much acceleration does a given bake temperature provide? Consider again our example. Our product has a desired 15-year lifetime. It's expected to operate an average of 2 hours per day, so the total operating time is 12,000 hours. Assume an average product temperature of 87 degrees centigrade. So, we'll bake at some temperature above 87 C. But what temperature and how long? From the Arrhenius equation, we'll calculate an acceleration factor. During baking, the rate constant K is higher than during regular operation. And time is the inverse of rate, since a fast process takes less time. The acceleration factor tells us how much faster we expect the product to age during baking than during normal operation. The acceleration factor is the ratio of the rate constants. Since rate is the inverse of time, this ratio is equivalent to the ratio of the corresponding time durations. If you double the rate, you halve the time. Once we have the acceleration factor, we can calculate the bake time. Let's derive the equation for the acceleration factor from the Arrhenius equation. First, write out the Arrhenius equation for the application, using K-app for the application's rate constant and T-app for the application's operating temperature. We have a similar Arrhenius equation for the bake, with K-bake and T-bake. Write out the acceleration factor as a ratio of the two rate constants and rearrange the terms. This is the acceleration factor. Notice how the pre-exponential term A canceled out. The terms in the acceleration factor equation are EA, which is specific to each failure mechanism. 0.7 eV is the value that I've seen most often. We'll talk more about EA later. The Boltzmann constant, a fixed value, and the temperatures for our accelerated lifetime baking and for our application. Let's apply the acceleration factor to our example problem. how hot and how long do we need to bake to emulate this product's lifetime aging? The bake time is the application lifetime scaled by the acceleration factor. And here it is, written out. When we plug in all values, we can see that using a higher baking temperature shortens the necessary bake time. And, as expected, it's a very nonlinear relationship. A 20 C temperature increase decreases the bake time by a factor of 3, while a 40 C temperature increase decreases bake time almost 9 times. I chose this example directly from the AEC-Q 100 document. AEC-Q 100 is a specification from the Automotive Electronics Council. It specifies tests to determine that a device, meaning a chip or integrated circuit, can be expected to give a level of quality or reliability appropriate for an automotive application. It's a widely used specification. I would guess that most car manufacturers require that most chips and critical systems of the vehicle comply with AEC-Q 100. In my example, I used the same application assumptions as this example from AEC-Q 100 and the same activation energy EA, with a nearly identical result. The 1,000-hour test duration listed in the AEC-Q 100 document is common in my experience. 1,000 hours is 42 days. Because the duration is so long, the test may be paused every few days to check for failures. The test is run on a group of units, and if they start failing early, that's useful information to have. Engineers can start working on understanding those early failures as the test continues to run on the remainder of the batch of test units. As a side note, AEC-Q 100 is for chips, and AEC-Q 200 is for passive components like resistors and capacitors. In summary, in this last section, we saw that the Arrhenius equation is exponential in temperature. The pre-exponential factor A disappears or cancels out from the equation for the acceleration factor AT. A higher bake temperature T bake allows for shorter test time, little t bake. Accelerated lifetime testing based on the Arrhenius equation is widespread. The automotive industry standard AEC-Q 100 embodies this methodology for accelerated lifetime testing, including the common 1,000-hour bake time. This is the end of video 1. Please continue the reliability lecture in video 2.